This video will summarize the design and construction of an engine bottom end assembly, also called a short block assembly. It will explain how bottom end parts are made and function in an engine. It will also compare and contrast different part designs. By understanding how components are constructed and operate, you'll be better prepared to service these parts and analyze part failure when repairing engines. This illustration shows a cutaway of a cylinder block in yellow. Note how the other parts fit into or fasten to the block. The short block includes the cylinder block, crankshaft, rod bearings, main bearings, connecting rods, pistons, wrist pins, and piston rings. The crankshaft converts piston motion into usable rotary motion for the vehicle drive line. The number of cylinders machined into the block determines if the engine is a 4, 6, or 8-cylinder engine. Here's a block for a V8 engine. Bare block refers to the cylinder block with all of its major parts removed. Here you can see the oil pan mounting surfaces, the main bore for the crankshaft, and the crankcase. Freeze plugs install in the side of the block after it is manufactured. Various surfaces are machined for sensors and other components. This cylinder block is partially hollow, which allows coolant to circulate around the cylinders. Passages in the head and block connect to allow coolant and oil flow between the two. Note the water jacket formed in the front of the cylinder block. A water pump forces a mixture of antifreeze and water through the block and head during engine operation. Here's the mounting surface on the front of the engine for the water pump. Oil passages are also cast and machined in the block. This is the main oil gallery that runs down through the center of the block. This main passage feeds oil to all critical parts of the engine. Screw-in plugs are installed wherever a passage has been machined down through the block. This animation shows the basic action of a lubrication system. The oil pump forces lubricating oil up into the main oil gallery, which then feeds down to the crankshaft and up to the valve train. Drain holes are provided in the center of the block to allow lubricating oil to drain down from the cylinder heads and into the crankcase. Various holes are drilled and tapped into the block like these head bolt holes. This is a dowel that helps hold and align the head gasket and cylinder head. On this overhead valve cylinder block, the camshaft installs in the center of the block. Cam bearings press fit into the block and provide a surface for the cam journals. Note the oil holes feeding into this cam bearing. Freeze plugs do not protect an engine from freeze-up damage. This is a press-in freeze plug. Here's a high-performance screw-in freeze plug. Also note the mounting pads for the motor mount. Many blocks have a Petcock, which allows you to completely drain all coolant from the block. Any surface that must seal pressure or fluid is machined smooth, like this mounting surface for the oil filter housing. Main caps bolt to the bottom of the block. They hold the main bearings and the crankshaft in place. High tensile strength main cap bolts secure the main caps in place. The crank journal is the surface that rides on the main bearings. The main bearing is a removable insert that fits between the main bore and the crank journal. Here you can see a main cap. After machining flat mating surfaces on the cap and block, the block is line bored to produce a precision hole through the main caps and block. There are various main cap designs. 2-bolt mains refers to a main cap that only has 2 bolts. 4-bolt mains are for high performance. Cross-bolt mains are another high-performance design, featuring 2 extra bolts through the side of the block to secure the caps to the block. With cross bolts, spacers are used between the bolts and the cap. A girdle or unit cap is one large cap that fits over all of the main journals on the crankshaft. Main bearing inserts, as shown, fit between the block main bore and the crank journal. A main thrust bearing is used to limit front and rear movement of the crankshaft. This rear main bearing fits in the back of the block and is larger than the other main bearings because of the flywheel and clutch loads. Here is the rear main thrust bearing. One insert fits into the block, the other insert fits into the cap. Here you can see a technician installing a rear main oil seal, which prevents oil leakage out of the back of the block. Remember, cylinder walls are machined down through the top of the block. The skirt is the side of the block at the crankcase. The block deck is the machined surface on the top of the block. The main bore is a hole machined through the caps and the block. The main caps bolt to the bottom of the block in the crankcase. The web is a reinforced area that supports the main bore. Here you can see an actual cylinder wall. This is an integral cylinder machined directly into cylinder block casting. Cylinder sleeves, or liners, can also be press-fit into the block. This is common with aluminum cylinder blocks. The cast iron sleeves are force-fit into the block to provide a tough surface for the piston and piston rings. Sleeves can also be installed to repair a damaged cylinder block. A dry sleeve is a thin wall sleeve that press-fits into a bored cylinder. The sleeve does not contact the coolant directly, but simply press-fits into the existing overbored cylinder. A wet sleeve is much thicker. Its outer surface touches the coolant. A seal is needed at the lower and upper end of the sleeve to prevent coolant leakage. Wet sleeves are not commonly used to repair cylinder blocks. They are used when the engine is designed and manufactured. This engine cutaway shows wet sleeves in a high-performance Corvette engine. The steel sleeves provide a very rugged cylinder wall in the lightweight V8 aluminum cylinder block. The crankshaft spins inside the crankcase. A crankshaft snout is machined on the front of the crank to provide a drive mechanism for the camshaft and accessory units. The main journals are machined and then polished to form a very smooth bearing surface. Counterweights are formed on the crank to counteract the weight of the spinning rods and pistons. They allow the engine to operate without vibration. The rod journals are machined and polished like the main journals. The connecting rods and rod bearings bolt around the rod journals. The rod bearings are removable inserts that fit between the rods and rod journals. Here is a rear main journal. As mentioned, it is sometimes larger to support the extra load produced by the clutch. The crank flange provides a mounting surface for the engine flywheel. A pilot bearing installs into the rear of the crankshaft with manual transmission-equipped cars. It supports the transmission input shaft. Note the crankshaft flange, pilot hole, flywheel bolt holes, the main journal, the counterweight, and a one-piece rear oil seal in this engine cutaway. The crankshaft snout normally has a key, which locks the camshaft drive gear to the crankshaft snout and prevents it from spinning on the snout. Crankshaft journals are usually undercut on their outside areas. This helps engine oil to escape from between the bearings and the crankshaft. Oil holes lead out of the crankshaft and to the rod bearings. The holes are chamfered to prevent wear on the bearings. This illustration demonstrates the oil passages in a crankshaft. Oil is pumped down into the main bearings. It can then flow through the crankshaft and out the rod bearings. Without lubricating oil, the rod and main bearings would be destroyed in a matter of minutes. During engine operation, as is demonstrated by this 4-cylinder crankshaft, the rods are exposed to tons of force. If they are not designed, constructed, and assembled properly, the connecting rods will fail. Connecting rods can be made of cast steel, stronger forged steel, or lightweight titanium or aluminum. The rod's small end accepts the piston pin. The pin slides through the hole in the small end of the rod. Most rods have an I-beam construction. The I-beam provides a strong structure with minimum weight. The rod's big end is on the lower end of the rod. It accepts the rod bearing. A rod cap fits onto the body of the rod. High tensile strength bolts secure the rod cap to the rod body. The rod cap and the rod body are a matched set. You cannot mix up caps on the rods, or engine damage will result. Both parts are machined within thousandths of an inch to provide an accurate surface for the rod bearings. For this reason, rods and caps are numbered. The cap number must match the rod number. Normally, these numbers are provided by the engine manufacturer. When the correct rod cap is bolted to the rod body, the inside bore is perfectly round. The rod's big end bore diameter is the measurement across the machined rod and cap as shown. The rod cheek is a machined side surface on the rod that contacts the sides of the crankshaft. Rod width is measured across the rod cheeks. The rod's small end diameter is measured inside the hole machined through the bushing or rod body. Piston pin diameter is measured across the outside surface of the wrist pin. Some rods do not have a bushing. This type of rod is usually press-fit on the pin. Other rods have a small end bushing installed into the rod body. A rod bearing insert, or rod bearing, snap fits into the cap and the rod body. 2 bearing inserts form one rod bearing. Rod side clearance is the measurement of how far the rods can move sideways when bolted to the crankshaft. Rod thickness or width and the distance between the crankshaft cheeks determines rod side clearance. A typical spec might be 10/1000ths of an inch. A press-fit piston pin has an interference fit in the connecting rod. The pin is locked into the rod's small end, but is free to move in the piston pinhole. A free-floating piston pin can move in the connecting rod bushing and in the piston. Snap rings keep the floating pin from sliding out and hitting the cylinder wall. Most engine bearings have a similar construction. A soft babbitt or outer alloy coating is plated over a hard steel backing. The soft surface allows small impurities to embed into the alloy coating. The steel backing gives the bearing its strength. An oil hole is provided to allow a film of lubricating oil to prevent part contact during engine operation. An oil groove can be used to disperse the oil around the main bearing and journal. Rod bearings, main bearings, and some overhead cam bearings use a lug to locate the bearing in their bore. The term free spread refers to the distance measured across the outside half of the bearing insert. Free spread makes the bearing lock into place when installed in the bore. When installed, the bearing diameter is measured across the inside of the bearing. Bearing crush means that the bearing is slightly larger than the bore. When bolted together, the bearing is compressed slightly and locked into place. A standard bearing has a factory-specified thickness and inside diameter. An undersize bearing is slightly thicker and would be needed if the crankshaft journals were machined smaller. A small clearance is needed between the journal and bearing surface to allow motor oil to keep the parts separated. Without a flow of oil into the bearing clearance, the bearings and journals would wear out very quickly, in a matter of miles. This is because tons of force can be applied to the bearings during engine operation. Bearing clearance is determined by subtracting bearing shaft diameter from bearing insert inside diameter. The pistons are exposed to tremendous heat and thrust loads. They must be very strong and lightweight. The pistons fly up and down in the cylinder while in contact with the combustion flame on the power stroke. For this reason, pistons are normally made of cast or forged aluminum. They are then machined to accept the piston rings, piston pins, and to allow engine oil to flow into high friction areas. The two top grooves in the piston accept the compression rings. The lower grooves normally accept a three-piece oil ring. Note that this piston has a groove cut to accept a snap ring for a free-floating piston pin. The piston pin boss is a thickened area around the pinhole. Here you can see holes drilled through the oil ring groove. This allows oil to flow into the center of the piston as the piston slides down in the cylinder and the oil ring scrapes oil off the cylinder wall. The head, or crown, is the top of the piston. Ring lands are formed by the surface area between the piston ring grooves. Here you can see a cutaway of the wrist pin hole and the pin boss. This piston has an oil hole drilled up through the pin boss. The skirt is the lower area on the side of the piston. Piston diameter is the measurement across the sides of the piston. If you were measuring actual piston diameter, you would measure across the skirt about even with the pinhole. Skirt length is measured from the bottom of the skirt to the lower part of the oil ring groove. Groove width is a measurement from the top to the bottom of the piston ring groove. Groove depth is measured from the ring land to the side of the groove. Compression distance is determined by a measurement from the center of the pinhole to the top of the piston. Deck height is a measurement from the top of the piston at TDC to the top of the block. This engine cutaway shows the piston ring installed on the piston. The piston rings have a very important job. The two compression rings must keep pressure from leaking out of the combustion chamber. The oil rings must keep oil out of the combustion chamber. Ring gap is a term that refers to the distance between the ends of the piston ring when installed in the cylinder. It is measured in thousandths of an inch. If the ring gap is too small, The ring could freeze and lock in the cylinder. If the gap is excessive, the ring may not be able to seal properly. Here you can see a 3-piece oil ring. The expander spacer fits into the groove first. Then the 2 steel scraper rings install on each side of the expander. Since the piston is a few thousandths of an inch smaller than the cylinder, it can move slightly sideways. However, since the piston rings are spring-loaded against the cylinder wall, they stay in contact with the cylinder to prevent leakage. As this animation demonstrates, the cast iron compression ring keeps cylinder pressure in the combustion chamber. The steel oil rings remove excess oil and return it to the crankcase. Good luck in your future study of auto mechanics.